everybody here is incredible. I've been here for probably, maybe 5-6 hours, and I've gotten to meet such smart and fascinating people. So it's wonderful to be here. It's an awesome conference, and I hope to come back to Austin again. This is a wonderful place. So as Mike mentioned, the title of the talk is Implementing a Large-Scale Identity Theft Prevention Solution Using the Cloud. That is very loaded, so let's unpack that. And I think basically what I'm trying to get at is a crash course in scaling code, architecture, and your team to process north of 50,000 transactions per second. And so to set the context of, and basically set the stage of everything that we're going to be talking about today, and I'm known, Mike didn't also include this as part of my hobbies and background, I'm known to talk a mile a minute. So this is going to be a relatively dense case study. I hope that's okay with you guys. We're going to be covering all sorts of stuff. So the outline of today will set some context, a little bit more about me, a little bit about what we're up to, philosophy about computation or computing philosophy, and then we'll dig into security because that's what this is about. It's LastCon for a reason. And then we'll dig into our architecture, our implementation, and then we'll finally close with some learning lessons. Pros, cons, and I'm going to try and be as unbiased as possible, but at the same time I'm going to try and be incredibly objective and honest with everybody here. So there's things in the slides. We've chosen vendors, we've chosen technologies. There's no such thing as a perfect fit. I want to be upfront with everybody and let them know the pros and cons that we've seen implementing a very large-scale solution. So let's start off with some context. So Mike already gave you a little bit about my introduction, a little bit more about me. I am, in fact, a quant. I study quantitative finance and economics, macroeconomics. I worked at NASA many, many moons ago, focused on computer-aided engineering, helped work on various flight projects, including the Mars Science Laboratory, the Space Interferometry mission. I then went to go be an InfoSec manager at MySpace. We all remember MySpace, this sort of social network that time forgot. And afterwards, went over to run technology and security at the BBC Worldwide. So if you're familiar with Doctor Who, Top Gear, I'll even throw this one out there, Dancing with the Stars, that's all BBC, and was responsible for technology and security across those domains with respect to mobile and web applications. And currently co-founder and CTO of Prevoty. So the elephant in the room is in fact Prevoty. And I just have this slide up here because this is not about Prevoty. And I want to make that really clear. We're really privileged to be a part of this community. This is not a product talk at all. I'm not here to sell you guys anything. We're not even going to be talking about the Prevoty products in specific. What we're going to be talking about is scaling and how we built what we built. But ultimately, we're a technology security company. We're headquartered out of Los Angeles. We're doing some really cool things with respect to application security. And that's what really forced us and drove us to adopt things like the cloud, and I'll put that in quotes for now, and you'll see why. So I truly, on top of surfing, on top of bass guitar, I really care about language security, commonly known as LangSec. I also care a lot about distributed computing, and hopefully you'll get a sense of both of those two things as we go, as well as data visualization. And so why me? Why am I here? What sort of case study am I talking about today? Well, we built, and we were really forced to build a large-scale computational engine and a large-scale computational system to process lots and lots of requests. We have to deal with customers that have peaks of 100,000 requests a second. And what we basically are delivering to them is an SDK where they can call the cloud or call our solution in the cloud whenever they want to process or generate things like tokens for cross-site request forgery, for authentication or authorization. They can call us when they want to sanitize cross-site scripting or content for cross-site scripting or sanitize queries to prevent against SQL injection. And so when you have these sorts of customers and you've got these users where the usage pattern can go from 0 requests a second to 100,000 requests a second, and that sort of ramp is only 5 seconds, you have to learn how to build resilient infrastructure. And that's what we're going to be talking about today. So let's dig right into computing philosophy. So these are some of my favorite images, and it may be a little bit difficult to see, but this is basically outlining the state of motherboards, and motherboards over the last basically 40 some years. And you can see all the way on the left in 1971 that we basically were only able to pack 23,000 transistors on a motherboard. Today, and this is not even recent, but today we have billions of transistors happening on these sorts of hardware components. Even the smartphone that you have in your pocket has billions of transistors. And so what basically happened over the last 40 some years is that cores became a lot more energy efficient. They became faster. They became cheaper to manufacture. And so this sort of core density basically amounted to a couple of things. Most importantly is that Moore's law really took effect. I think back in the 80s, I remember when I was mucking around on an old DOS-based system, and I remember every year consistently having sort of looking at sorts of trade show periodicals and whatnot, seeing how we were sort of upgrading and doubling our processors every year. And we sort of hit a brick wall. And as a former gamer, it was kind of frustrating, right? When you wanted to run the latest and greatest games and you sort of hit a brick wall because the processors weren't in fact getting faster and they weren't really improving. What ultimately started happening was that we started seeing the constraints of Moore's law and applied that to basically stacking all of these different cores. So we went from single core processors to dual core, to quad core, to 8 core, et cetera, et cetera. And the interesting thing is, in the state of computation, we started to solve bigger problems because we had access to more and more technology. And supercomputers, and everybody knows about Cray. There's all sorts of fun things and fun photos about that stuff. If you're into Kanye West, there's a fun play on Cray with one of his songs, and that's all I'll say. There is a trend that we've seen, which is we've gone from large-scale supercomputers to grids, and we saw grids be a real thing in the last 10 years. The idea of, look, we're not really able to get 80 cores in a really efficient way into a single server. It's not really possible. But instead, let's fan this thing out to multiple physical instances. But grids have a significant issue, which is they're mostly predicated on hardware. At least a lot of traditional grids were predicated on hardware-based solutions. And those have insane limits. Most importantly, there's a physical boundary. There's a physical limitation to how you set that thing up. Well, fortunately for us, this happened, which was the idea of being able to take everything that you're running from a computational perspective physically and shift that into a virtual space. And that's ultimately what we think of the cloud. That's ultimately what it is. It's basically compute processes, compute instances that are running somewhere else other than the environment that you're in right now. It's easy to spin up. And this is sort of shifting the economics a little bit, but you can go from 0 instances to thousands of instances inside of 10 minutes. You could never have done that before. Trying to get your grid up before, and I remember having to do this at places like MySpace, at places at JPL, at NASA. If you wanted to build a grid, you'd have to procure lots of hardware, you'd have to set it up, you'd have to bring your own networking gear. You don't have to do that anymore. Now if I wanted to start performing and starting to do data analysis on a large scale, I absolutely can for relatively low cost. So cloud computing has been great for several reasons. First of all, if you ever wanted to do asynchronous or latent analysis on large scale or larger data sets, and large data sets not being megabytes, but large data sets being petabytes of data, terabytes of data, you can do that for a lot cheaper. Today, a petabyte storage costs around $200,000. That's it, for storing a petabyte today. That's an insane amount of information that you can store relatively cheaply. And the cool thing is, if you wanted to put that in the cloud, you absolutely could, and you can shard and fan that data across. So if you wanted to do distributed MapReduce, you absolutely could. So we have this thesis, and it's a thesis that when we were starting the company of what we believe in with respect to computation. And to sort of put all of these things together, we thoroughly believe that the people who are going to win the sort of next generation of computing will be those who take advantage of all the core density in the world. So I know it's a grandiose statement, but if you think about it today, your laptop may have 4 cores, may have 2 cores, doesn't matter. A lot of your traditional programs and applications can really only take advantage of one of those cores. So if you're building your application in C or C++, if you are not programming it with correct threading or a way where you can basically take your process and have that fan across multiple processors, you're not taking full advantage of all the computational resources at your fingertips. So the cloud's been interesting because now I can spin up a quad-core box, I can spin up an 8-core box for very low cost and in a very quick amount of time. But the problem is the application and the software really hasn't changed to take advantage of that. Traditionally, the solution has been if I've got a 4-core box and I've got a simple process, I just spawn that process 4 more times. And so it doesn't matter. I'm guaranteed that each individual process or each individual instance is going to take advantage of a particular core or a processor. So we basically realized that this is going to be the big thing. How do we take advantage of all these cores, especially when we've got access to all these things? So the case study that we're going to be talking about today is starting with Amazon Web Services. And we'll dig a little bit more into this, but Go. It's a programming language developed by Google. And the way I like to think about it is if C and Python met at a bar, maybe on Rainy Street, and they had a kid, that's what Go would be. And, and basically, it's a language that has very robust asynchronous abilities. And I would say concurrency primitives is probably the correct way of phrasing that. And we'll go into that in a second. So why AWS? For us, it's a strong ecosystem. Our team was fortunately a little bit friendly, or a little bit more familiar, I should say, with AWS's offerings. Very robust services out of the gate. So everything from DNS to load balancing to notifications to queuing engines. We'll dig into some of these components, the pros and cons of all of these things and learning lessons. It's also a predictable and competitive cost model. I think all of the cloud providers can say that, and it's certainly true. Whether you go from Rackspace, AWS, or Google Compute Engine, everybody's sort of competing with each other. And when these cloud providers compete, we all win. It's awesome. The other thing is it's also predictable. When you choose any one of these cloud providers, it's absolutely predictable if you have to deal with a certain amount of workload. Now, why Go? So I already mentioned it's got an awesome concurrency model with respect to Go routines and channels. It's an alternative way of thinking about your problem. So traditionally, you have to think about threads. You have to think about joining threads. You have to think about thread synchronization. And it's extremely tedious, and it's often error-prone. When you're developing a robust application, sometimes it's problematic of who's the producer, who's the consumer, am I locking, am I deadlocking? You run into weird places of contention when you're developing your application. Well, Go ships with these two primitives that make life amazing for us. First is Go routines. Go routines is basically an ability to execute a function that's independent of your current running process. So if I basically wanted to, I could give it a function and just say, go do this in the background somewhere else. That's it, and completely forget about it, and my application continues to function as it is. The second is channels. And channels allows us to basically communicate just by sharing data. So channels, and the way to think about a channel is just a buffer. And the idea is that if I wanted to communicate between different Go routines, I could do that just by putting a data that's strongly typed, or a data blob that's strongly typed, into a channel and have that be used by anything else. So you can have buffered channels, you can have very large channels, but it gives you an ability to communicate. And it's absolutely important when you're designing and developing really large APIs and large workload systems where you need to respond back to your customer sub-second. And so when you need to do that, it means that you can't just do all that work up front. You need to be able to fan out, distribute, send your work to a channel, send it to a background thread, do the processing you need to, but just quickly respond back to your customer and let them know that, okay, here's your result, everything is cool. The other fun thing about Go is it's, aside from it being strongly typed, it also compiles, and it compiles into binaries, and it makes it fantastic. So if we're deploying across customers, or if we're deploying across multiple operating systems and architectures, we can do that very easily just by having a different runtime. And I'll show you some fun stuff in a little bit. I put Unicode down here, and this is a real big one for us. So how many people here have some sort of scripting language background, like, for instance, Python? Yeah. So how many people have been burnt by Python and Unicode and strings? Yeah, it's pretty insane, because getting Unicode right is an incredibly difficult problem. And if you're using scripting languages today, it's very, very difficult. And these languages are getting it right, but they sort of go through various stumbling blocks. Go ships with almost the complete Unicode specification. So it's got the full UTF-8, UTF-16 table, or tables, which basically means that we can map character sets, which also means that if we see a UTF-8 string or a UTF-8 character, we can understand it as UTF-8 and not have to do any funky conversions, or worry about buffer overflows, or worry about not missing something. Now, shifting gears a little bit, security philosophy. So here are the true challenges that we see from our side, and I think from being a part of this industry now in the security space for more than 10 years, it's something that I've definitely noticed. One, detection has improved. You've seen a huge sort of effort and initiative on the detection side of things. So you've got novel technologies and newer technologies, companies like Contrast, for instance, that are doing some really cool things in the space of IAST. But you also have this increase in large number of backlogs and difficulties and vulnerabilities. And how do you prevent against this stuff? How do I sort of take my thousand issues and go down to a reasonable set? Because that may be unreasonable for my team. We're also still relying on past definitions and signatures to do a lot of our work for us. So relying on regular expressions, string replacements, just to understand whether or not a query or a fragment contains the word delete from. We don't know where that's going. We don't know what that's going to do. We don't know if it's going to hit a database engine or not, but we're still using technology to determine whether or not that's a way that's going to execute SQL injection. And the key thing down here is that anybody can be an attacker. If I wanted to today, I could grab an open source piece of software and launch millions of attacks on any service whatsoever. And this sort of combines what I was just talking about from the computational side, which is that someone anywhere in the world, it could be a kid, can just go ahead, download some open source software, and if they wanted to craft a ton of unique payloads at your web service or your web application, they could do that today. And they could DOS you, they can DDoS you, and we see this happen all the time. And there's some fun anecdotes that we can share about that. So when it comes to preventing these kinds of attacks, you need two things. You need content and you need context. So content being the actual content itself that's going to go back out to a browser or the database query, but you also need context. Where is this going to go? Where is this coming from? Where is this payload going to end up on a web browser or in my HTML document? Is it going to be out in the DOM itself? Is it going to be inside of an attribute? Is it going to be inside of a JavaScript variable? Where is this actually going to go? So to do payload analysis, you've got to develop a compiler. And when you talk about developing a compiler, there's two very fundamental aspects of developing a compiler, which is tokenizing. So you need to be able to iterate rune by rune. And the second is you need to be able to parse. So after you build up your token stream, you have to be able to parse that. And you call some sort of function afterwards to evaluate it, and that can return anything you want. And now the reason why I'm mentioning all of this stuff is part of what we do requires us to have all of this. So to tie everything back to why we built our stuff in Go, Go makes this a lot easier. Having full and amazing first-class Unicode support is amazing. And being able to do this, and Go really allows us to do this and express this code that would have ordinarily been maybe 30, 40,000 lines of C. Go allows us to really express this at a fraction. So we save 90% of the lines of code, and we get all the safety of Unicode, plus we get a robust asynchronous model. Now, when we talk about context, there's several ways you can do that. One is through bytecode injection, agents, plugins, or shims, or the other is when you provide it to an SDK. And this is a really great segue now into what we actually mean by parsing and content analysis. So this is something that runs through our parsers. This is what we yield back as an example parse tree, for instance. And it looks like a nice, pretty tree of all sorts of different nodes. But when you run it through a parser, when you tokenize this, when you parse this, you're able to sort of identify interesting constructs. You're able to identify what are some bad nodes and what are some good nodes. For instance, a div tag may be a good node, whereas a script tag may in fact be a bad node. Now being able to do this on the server side can involve lots and lots of resources. And it also involves not only heavy on the compute side, but when it comes to analytics, when it comes to storage, it's a lot of work. So now let's dig more into how we built what we built and what this looks like overall. So this is the first time as a company we've ever talked about this. We've ever talked about the infrastructure that we have, and we've really drawn some sort of diagram that outlines all of these components. And we'll actually, in this presentation, we'll dig into each one of these. And this is why I was saying expect for me to go a mile a minute as we go through all of these different components. Because you'll hear true stories and basically pros and cons of implementing a large-scale solution like this. So this is Prevoty as it's deployed on a large Amazon system where you've got DNS provided by Route 53, load balancing, compute instances, touching things like DynamoDB for key value storage, when and where, why would you ever need key value storage, why is that different from a relational database, what is all of these different components. So before we sort of dig into that, there's this concept in cloud computing of regions and availability zones. It doesn't matter which provider you use today, there is an inherent concept of your stuff that you're developing, the sort of network topology is living within some sort of region, whether it be West Coast, East Coast, some data center. So when it comes to this stuff, and what we've learned is that going multiple availability zone inside of a region is pretty trivial. It's not that hard inside of one region to scale out. What's actually a significant pain point is when you start and when you try to figure out how can I coordinate all of these different regions together. So if I'm storing data and I'm storing 100,000 requests per second, or the analytics from 100,000 requests per second in East Coast, how do I synchronize that to West Coast? And how do I keep that at very low latency levels? Also, aside from the sort of synchronization challenges that you have, how do you automate this? How do you automate failover? How do you make sure that the region that you're deploying or the code that you're deploying to one region is consistent within another region? It's a significant challenge, and it's something that we've had to face, and we'll share all our experiences with that. So we'll start with Route 53, which is DNS. So first of all, in the cloud, actually, I'll rewind for a second. How many people have had to set up DNS pre-cloud era? Yeah. Remember that? Pretty crazy, right? And the key thing, and I used to have some funny photos in here, and I removed them, but my favorite one is Picard, and it's the Picard meme. I don't know if you guys have seen the Captain Picard meme, and it's just flush the DNS. And it's a great example of how far we've sort of come, because I remember back in the day, we would spin up another compute instance, and we'd try and set DNS up for that. And we'd have to constantly go back. Did you flush your DNS? Did you add it to your host file? Is DNS propagated yet? Well, the cool thing about using the cloud is that you can combine your infrastructure with DNS. So that's a thing of the past. You never have to worry about flushing your DNS anymore. You never have to worry about, well, what if I change my load balancer? What if my load balancer changes addresses? The simple idea that you can connect an A record or a C name with a load balancer is incredibly powerful. It also means that when you're deploying across multiple regions, you can start to do some fun things like latency-based routing. So in the cool case of AWS for us, we have East Coast and West Coast, and we do latency-based routing. So depending on where our customers or where anybody is calling us from, if they're calling us from Chicago, they're going to go to the closest one. And the closest one isn't just going to be based on geography, it's going to be based on timing, because they're going to recognize the fastest response that they can get back, and they're going to always go to that one. So this sort of route sampling that ends up happening on the DNS side. It's also convenient and cheap when you start connecting DNS to your cloud provider. Has anybody here played with tools like Ultra DNS or any more robust offerings? It's incredibly expensive. You would typically have to spend hundreds and hundreds of thousands of dollars to manage DNS. Using any cloud provider like Rackspace or AWS, what's really neat is that you can have them basically run your DNS for you, and you can support thousands and thousands of queries, and you can do that for cents, not even dollars. So private clouds. So there's a concept that's sort of emerged, which is that you have a cloud and you have what's called a private cloud. And if we unpack that a little bit, a private cloud basically means you have an ability to really design your network and service topology. So the one negative thing I would say that's happened with cloud computing is that everybody thinks that they can do it. And everybody thinks that they can manage and set up their infrastructure in a secure way. The problem is you have people who are building out these robust networks, or what they claim to be robust networks, without knowing anything about security, without knowing anything about basic networking. And so if you were to go to an average software developer today and say, well, I want you to deploy this service, but I want you to deploy it on a particular subnet, and here are the sort of IP table rules that I need you to apply to this, they're just going to look at you with a blank face, because it's not what they do. Unfortunately, what we are seeing today is, because it's so easy and because there's just such low barriers to jump in, we're seeing developers make a lot of mistakes. And it's easy to shoot yourself in the foot when it comes to this. So they encourage you, and you're certainly encouraged to go and evaluate something like the cloud or services like AWS, for instance, but it is so difficult if you've never done it before to get it done right. And I would say that it's something that if you're looking to build out on your own, definitely look at bringing on someone with some network experience, because it's not trivial to set up. The other thing that we've learned, and this is going to sound a little bit strange, and we're certainly curious about this, is a VPC is fantastic for sort of constraining security groups' input and output, The other thing that we've noticed is that the request response times are a little bit slower, and it's a little bit slower consistently, whether we're in East Coast or West Coast. And we're working with guys at Amazon to sort of figure out what this is and what's the sort of motivation behind it. But it's something to consider when you're building out a VPC. What do you choose to have in your VPC, or what do you have outside of the VPC? And do you have certain services that are scaled and deployed a little bit differently? And there's no good reason not to use a VPC. So your traditional security groups are really just constraining everything that's coming into your environment. A VPC also allows you to articulate communication amongst all your nodes within your environment. And this is a really important thing. So let's say you're building up or you're deploying your own instance of memcached. Well, you deploy your own instance of memcached, and you typically say with a security group that I want to have access open to these particular ports, and here are the sort of security groups for it. Well, the pain point is when you have multiple sort of groups that come up that also need to rely on memcache, you're constantly updating security groups when you could just rely on the subnet itself. And just by having proper network topology, you can sort of avoid a lot of the pain. So shifting gears a little bit to load balancing and what we've learned from this process. It's intuitive. It's easy to spin up a load balancer. Gone are the days of having to buy and rack and stack, hundreds of thousands of dollars of network gear. At this point, I can get a pretty decent load balancer. It's probably Nginx or HA proxy under the hood. Now, I have this here. SSL termination is nice. Sure, it's nice to have SSL termination, but you may not be able to do it in your environment. There's certain elements of Amazon's ELB that may be prohibitive, especially when you're looking to run an enterprise that has to achieve a certain level of compliance based on logging, based on metrics, based on if I terminate SSL at the ELB and my process fans out to EC2 instances, well, that's not encrypted at that point. Does it need to be encrypted? And again, it all depends on your use case. It depends on your organization. Also, load balancers lack static addresses. And a fun little anecdote, because it lacks static addresses, sometimes you may work with organizations, or you may work in your own large organization with various teams that need to whitelist addresses. And you don't whitelist DNS. People whitelist IP addresses. Now the problem is you would typically whitelist an elastic load balancer, or you would whitelist a load balancer altogether, but you don't get that ability with something like Amazon. You don't get that ability with a lot of cloud providers. And it makes it really difficult when it comes to that. So if you fall into any of those categories, it basically turns into bring your own load balancer to the table. So what we've understood and what we've realized is, aside from Amazon offering and running their services, we bring our own to the table. And it's something that we've realized that a lot of companies and a lot of people actually do too. Or you end up using IP tables and you do some really cool things with routing. And we can share some fun experiences with that.
What kind of load balancer do you bring in? It's not EC2. What kind of load balancer do you bring in?
So it depends, HA proxy or Nginx. Yeah. So HA proxy now has SSL support, which it didn't for a long time. On the EC2 side, so EC2 is kind of the heart of AWS. It's where you spin up compute instances, take an image, an SSH key, and I call it party time, because that's exactly what it is. You SSH up, and you can do whatever you want to do. It's your own server to mess with. Now, there's a couple of things that most people sort of get wrong, which is you sort of choose the size of your EC2 instances based on how much CPU and memory you need, but you also have to reconsider the networking needs as well. Because if you have a lot of data flowing in and out of your compute instances, believe it or not, a medium or a large, even though you're only seeing 1% CPU consumption, is not going to cut it. You're going to drop packets. You're going to drop requests. So you have to also size for the network. And finally, and we'll dig into that a little bit, EC2 instances aren't created equally. We've spawned instances that have gotten a notification about 10 minutes after we've spawned them from Amazon saying, oh, by the way, this is a bad instance, we're shutting it down. And that's it. I mean, it's pretty ridiculous. You're very lucky if you have an instance that can live 24 hours plus. At least that's the way we look at it. So our API, it's constructed fully in Go. We deploy binaries. It's a RESTful engine. It communicates with all the appropriate AWS services that we talked about. It's also running on compute-heavy instances. So we basically deploy our services to 4 core boxes. We found that it's the right price point for performance based on everything that we've seen. And this is a little snippet of Go code. And so what we're basically articulating here is runtime, set the max processors to runtime the number of CPUs. So get the total number of CPUs that are available on this service, and basically instruct Go when it starts up that, hey, all the work I'm doing for the Go routines and all of its channel work, spread it out on all of these processors. Spread it out on all of these cores. And that's it. That's one line of code. I don't have to manage 4 instances anymore. I don't have to worry about synchronization. I don't have to worry about anything. I just call this one line, and that's it. Batteries included. Just works. So Bastion. So Bastion is our jump-off box. It's our NAT. It's nothing more than basically a way where we can get into our environment. It can traverse all the availability zones. It can go across different regions as well. It runs various cron services and runs all sorts of security keys. Nothing really special. Everybody sort of needs a NAT. Everybody needs a jump-off. If you don't want to open up all of your servers for access, you kind of need one entry point, and Bastion is that for us. Smart Cache is a really cool technology that we wrote at the company. And the reason why we wrote it is when we have companies or we have customers that peg us at hundreds of thousands of requests a second, it's hard to keep up. When you want to start to store the analytics, when you want to start to store the transaction levels, it's really difficult to store all that stuff. So it's basically the best of a cache meets the best of a queue. It does in-memory aggregation and in-memory analytics compaction. And it allows us to basically collect a bunch of metrics, compact it down based on key, serialize, and write that data back out where it needs to. So a little snippet of code for this. We basically iterate through our analytics caches. This is a snippet of actual Smart Cache code. What we'll do is we'll loop through the caches. We don't care about the key itself. We just take the analytics. We JSON encode it, JSON.marshal on it. And then we have an analytics queue, and we send the message off to the queue. And whatever happens on the other side happens on the other side. But this is a snippet of how Smart Cache works in the context of our API. And there's a little thing on the bottom, sleep 10 seconds. So basically, we store everything for 10 seconds, and then we drop everything back out. Now, on the data side, so it's really difficult to manage databases on your own, especially when you're a small organization. And there's something that we absolutely love, which is if there's an ability for us to offload this work, and which we did in this case. So giving our data to Amazon or having Amazon sort of manage our databases for us has been amazing. So there's a huge trade-off, though, and it's really important to be upfront in terms of convenience and performance. It's incredibly convenient to have them do it for you, but there is a huge hit on the performance side. Running and managing your database on your own EC2 instance is going to be a lot faster than having them do it for you. Also, there's a nice little thing about relying on solid-state storage. So that's now something that's possible. So if you have a heavy amount of writes and reads, you can do that. So DynamoDB is another technology that we use. It's our key value store. So not everything fits into keys and values. Certain things do. So the title of this talk was around basically preventing large-scale identity theft. And that basically implies tokens. So how do we set authorization and authentication tokens? And today we set them, we generate them in Go code, but we rely on DynamoDB to store all of this stuff for us on the server side. And it basically means that we don't have to store anything. We don't have to manage a cluster of Redis instances. We don't have to manage any key value stores or trying to do synchronization. Amazon takes care of this for us. It's incredibly fast. And from our own individual tests, depending on how you sort of scale up your read and write units, which is their cost model, you don't necessarily need a cache in front of DynamoDB. And so for generating something, it's pretty trivial to generate any variable that you want to. Just sprint f your payload together, take the output of something like this, and that can basically be your key when you're communicating back with DynamoDB. SQS is a queuing technology that we wrote. And SQS is basically a way where we can rely on Amazon to do asynchronous aggregation. So SQS itself is created by Amazon, but we've built our own wrapper on top of SQS. So the API that we have when it's communicating back to SQS ships off a ton of analytics, which is those JSON blobs that you saw earlier. And SQS hits a dequeuer, or there's a dequeuer that talks to SQS, does whatever work that it needs to do, and sends data back. So an API, and this is actual Go code again from what we run in our environment, is pretty straightforward. We get access to a queue, and we send a message to a queue. That's it. 2 lines to do anything that you want to do with a queue in terms of sending a message. And in terms of dequeuing, also incredibly simple. On the queue client, just receive messages. And there's a caveat here. You see this hard-coded number 10, which is, why is that hard-coded as 10? Because believe it or not, that's the most you can get from Amazon on a single queue dequeue, which is insane. You only get 10 messages at a time, which means that you got to run this thing in a while loop. And the other thing is that it's not ordered. And we learned this the hard way. Amazon's SQS is not ordered at all. In fact, if you were to run a test on your own right now where you basically enqueue the entire alphabet, it's going to come back totally haphazard. We learned this the hard way. SNS. SNS is a simple notification service. It's basically a way one of the ways how we set up alerts on our EC2 instances. Nothing really too specific here other than we can set CPU memory thresholds. You can also set up network thresholds. So if you want to be alerted at any time when something looks rogue or something crazy is happening in your environment, you can get that sort of intelligence back. In terms of deployment, and this is also a fun one for us, we started using a tool called Fabric very early on. Fabric is a tool written in Python, and Fabric plus Bodo allows us to sort of deploy services at a large scale. We went from Fabric to an open source project that we threw out there called Prevoty Deploy, which is basically Fabric written inside of the Go language. And most recently, we've gone from PD, or Prevoty Deploy, to Ansible, which is the technology. We run deployments locally. We deploy things to prod, either from our own individual servers or through Bastion itself. We also have a concept of lifecycle deployment. So the steps are provision, setup, deploy, promote, and terminate. And the really simple thing and wrapper that we put on top of it allows us to specify things like this. So if we wanted to deploy code, we basically give it a group name. So I'm doing a full deploy on API. And you see these sort of flags, -S, -E. And what that basically implies is that at any point, we can pick up from any step and run it all the way to the end. And if we specify the gate at the end, then it's going to run specifically to that. So in the last few minutes, I kind of wanted to just sort of go over a couple of learning lessons and a couple of things that we took away from this process. Everybody has oh crap moments. Your instances will die. Your availability zones will die. Your regions are going to die. It's inevitable things die in the cloud. And the other good problem that sometimes happens is that you have users and customers that sort of can have peaks and valleys. And you need to be able to respond to those sort of things. And being able to build automated systems around that is also significant. Building a service-oriented architecture like the one that we have is great for reusability, but it's insanely difficult when it comes to debugging. If you have a problem anywhere in the chain, it's very difficult to do. And so the key thing is to build mock services. So if you're relying on something like DynamoDB locally, you got to build a mock for DynamoDB so you can prove that it's doing what it should be doing. It's a lot of upfront work to do. And we did it, and it's one of those things that we look back on now and say, well, was that actually a good choice of time? Was that a good balance? The other thing that you have to rely on is centralized logging and metrics. So there's got to be a way where you can, across all your instances, log particular payloads, pull it back on the other side, and do some correlation as to, hey, why didn't my API server actually enqueue this thing to SQS? There's another feature of Go that we are using now, and it's because of the weaknesses of SQS. So our goal is to be completely off of SQS altogether because of the limitations of only 10 requests and things are weakly ordered. And we're building something on top of NetRPC. NetRPC is a Golang feature that allows you to construct RPCs, batteries included, clients and servers, without having to worry about serialization or deserialization code, ever. It's wonderful if you have to start coordinating amongst nodes. And so registering an RPC is pretty simple. You register an RPC, you tell it what protocol you want to use. It could be HTTP, it could be TCP. You specify a port. The server side, this is an endpoint for how we could build a cache on top of RPC. So you put an item, it just key value, pretty simple, send an acknowledgement back. And then on the client side, if you were to build on top of a local RPC, this is what that looks like. You just build something, or you create a function that is basically a pointer to a structure, and what it's doing is it's calling RPC.put, the same server-side method that you saw before. So the key takeaways on the Amazon side is that nothing lasts forever. Again, you're very lucky if it lasts more than 24 hours. We've certainly seen the pain of we've tried to deploy services, we've tried to deploy topologies, only to be told that, hey, it's corrupt, it's bad, or we've got to take this thing down for maintenance. The last few weeks have been very fun in Amazon land, if you guys have been following all the vulnerabilities that have been coming out. Network failures happen all the time. EC2 instances IPs change a lot. Use elastic IPs where you need to. And also, if you haven't made the move from classic EC2 to VPC, you absolutely should. There's a lot of benefits from it. Now, testing, because we didn't talk too much about that, but we make sure that we run everything through unit tests, integration tests. There's sort of network load tests that you can run. We've identified a really cool tool called Vegeta, also written in Go. So if you're a fan of Dragon Ball Z, it's exactly named after the Dragon Ball Z character, or the Saiyan, Super Saiyan, I guess. And then there's Selenium tests for front-end services. We have not gotten to continuous integration yet. It's something that we hope to get to and tie it back into the Ansible deployment system. If anybody here has got some good feedback on building CI models in the case of security or in the security landscape, would love to talk to you after this talk. Performance is significantly important to analyze, especially when you're having to deal with 50,000 requests a second or 100,000 requests a second. So we have a really cool ability in Go where we can generate things like call graphs. And we have an ability where we can just sort of visually spot the main point or the main issues in our code base. So here's an example call graph that gets generated by Go. And this gives us a really good opportunity to go back in and to see, well, maybe we're spending too much time on our hash insertion versus our string traversal. In terms of benchmarking, Go also ships with some really cool tools as part of its test framework. So a thing called benchmem and benchtime. So in the case of running an algorithm or wanting to test a particular function, this is basically the result of it. You give it a total number of time, how long you want the sort of test to run for. So if you wanted to run your test for 10 minutes or 5 seconds, you specify that, and what the test tool will do is it'll try and run that function as many times it can in that window. And then it keeps track of how much time it took to run that, how many bytes per operation, how many allocs per operation, and you get this beautiful sort of blob that comes back from running the test process. Deployments, the key takeaway that we learned from this is that they should be noisy as possible, so everybody on the team and everybody in the company knows that you are deploying code right now. And also doing it in a way where we're not harming our existing environment. So when we deploy code, we basically spin up a new load balancer, we spin up new instances, we connect those things together, and then we can rely on tools like Route 53 for DNS. So if we wanted to fail over, we could fail over a different model for deploying code, but it allows us to have sort of zero downtime deployments today. We wrote a tool called Hulkster. Hulkster is an IRC bot, and this is zombie Hulkster, I guess, so that's funny. But the idea behind that is we're able to tell everybody in the team when we're doing anything critical to our environment. So if we make any change to our cloud environment, everybody who's sitting in an IRC knows immediately. Hey, someone just adjusted the security group. Someone just added this new node. There's a new load balancer in the pool. Every small action that we take gets sent into the IRC channel where everyone in the team knows immediately. So the closing slide and the key thing that we took away from this, and I'm sure you guys have gone through this as well, trying to scale an unknown platform is an art, because you have no idea what you're doing at that time. When we started, we had no idea what we were doing. We had no idea what our pattern and our request pattern usage was going to look like. We had no idea where the hotspots were in our application. The goal is to know every single part of your stack so you can turn it into a science. And a science means that you can build automated tools. A science means you can diagnose problems, you can identify hotspots in your code, and life gets so much more easier. And we think we've gone through this sort of transition, and I really hope that sharing some of these anecdotes, sharing a little bit more about our infrastructure was somewhat helpful around how to deploy and build services in the cloud, and sharing how we've made sort of the ambiguous a little more deterministic, I should say. So thank you guys very much for the time.
Well, one of the reasons that I work as a contractor, not a full-time employee, is because I would be the guy to tell the boss that he was out of time 5 minutes ago, okay? But he's really undeniable. He does have a table. Prevoty is in the vendor hall, so you can take your questions there if we don't get too much done here right now. We have time for maybe 1 or 2 quick questions, something you'd like to direct and focus on right now. You need the microphone so that you're recorded for the presentation.
So how much of all of your infrastructure is in the cloud? Is it 100% what you described, or do you still have some on-prem or data center?
100%.
Given that SQS has a 64K limit per message, and since you're waiting 10 seconds, does your function that enqueues messages also divide messages up into multiple SQS?
That's an
events?
awesome question. So what we basically do is we compact integers, so we don't store the original content, and so everything that we're storing is anyways under 64K.
Two quick ones. Did you consider Erlang? Because Erlang.
Yes.
Yeah, I was just wondering about the language selection.
So
And-
yeah, so we started when I was looking at building out the technology very early on. Started the prototype in Python, and went from Python to Java. Made the leap because of Unicode issues, and Python 3 wasn't heavily supported 4 years ago. There weren't that many sort of libraries that were adopting it. Java just seemed a little too heavy, and Go seemed more logical. We built a prototype in Erlang very early on. We love the concept of OTP. Makes a lot of sense. Amnesia is a really cool tool too for data storage. Key thing that we learned from that was string parsing was a nightmare. And trying to deal with Unicode and Erlang was such a pain, where we sort of realized that it was going to be better for us to pick a language that allowed us to spend more time on control flow rather than accurately parsing characters.
And what instance type did you use for Smart Grid?
Smart Cache? So that's a C3 large.
Okay, cool. Thank you.
Thank you very much. It's really been an honor and an opportunity for all of us to learn here this afternoon, and he has a table in the vendor hall. You can follow up there if you'd like to. Thanks again.
Thank you.
Thank you.
Appreciate it.